All right, so I'm here today to tell you a little bit about my perspective on geometry. Geometry is perhaps the most ancient mathematical field, at least here in the West, where the geometry we learn in school was already pretty much complete over 2,000 years ago in Greece. Of course, over the intervening centuries, many more mathematicians and artists and physicists and philosophers used and expanded upon the geometry of Greek, the geometry of flat space, the geometry of the Euclidean plane, named after Euclid. So I will call it that a lot throughout the talk. But what I want to tell you about today is the story that comes after that. In the last 2 centuries, geometry has really changed. You'll notice a lot of main characters from Germany in this talk. You all had a big, big play in this a couple centuries back. So starting with the work of Gauss, in expanding our view of geometry from flat space to more general curved spaces by really just taking the geometry of landscape seriously. Here's a picture from near my house in Northern California, up north of the bridge. And you can see the landscape is not flat. It's not approximated by a Euclidean plane. It's really rolly and bendy. And Gauss, in his works, actually doing surveying work, worked out differential geometry to take this seriously as an actual geometric space, the landscape around us. This discovery was taken by Gauss and others, expanded upon, where other abstract geometries were discovered. I'll talk about this space, hyperbolic geometry, a lot later in the talk, as a first space that's truly beyond Euclid's vision. This work was then generalized by Gauss's student Riemann and employed by Einstein in really transforming our understanding of the world around us, finding that while we've imagined the world as though it were flat for thousands of years, really this abstract mathematics that's been discovered recently is essential to understanding what's really going on. So my goal today is to share with you a really high-level picture of where this has went even since then. In the last 50 years, say, geometry has, well, I'm biased because I love geometry, but geometry has kind of taken over the mathematical world. It's found places everywhere. Geometry has found essential applications in topology, in physics, in data science, and so on. So my goal is to give a high-level picture. I'm not going to focus on any particular theorems today. I'm not going to prove any one result to you. But what I want to do instead is give a mathematician's view on what happened in the centuries since Euclid and led to our modern perspective. And with enough time, if I speak fast enough, I will share a little of the applications that are both dear to my heart and important to work here at HITS. So to start with, what's the big change? What's the one big idea that we came up with to move beyond the geometry of the Greeks? In my perspective, that idea is encapsulated by a number called curvature. And I want to explain to you how mathematicians can think about such a number. How do we tell if a space is flat, like the Euclidean plane, or if it's essentially not flat, if there's no way to take your object and flatten it out onto the table? How can we check mathematically? And a beautiful idea is to use the most simple shape around, use circles. Starting at a point in flat space on the Euclidean plane, we all know what are the circumference of circles of radius r, c equals 2 pi r. Circumference is related to radius by a linear scaling factor. So I've drawn a graph here of that relationship. You'll see the x-axis is radius, the y-axis is circumference, and we have a line of slope 2 pi that's encapsulating essentially how fast space grows as you move away from a point. Starting in the middle, as you expand circles larger and larger, we see how big they're growing by that linear graph. This is what we're going to take to characterize the geometry of the Greeks. This is the speed at which space grows when you move away from a point. But once you think this way, look back to one of these hilly landscapes in Northern California. If you were standing at the top of a hill and you did the same thing, you laid out a string around you and you dragged the string around the hill to trace out a big circle, you could measure the circumference of that circle on the hill, and you could measure the radius on the hill, the length of your string. And you could figure out what is the relation between C and R, and you could plot it on a graph. And if you did so from the top of a hill, you'd get a graph that looks like this, a graph that grows slower than linear. Actually, if your hill's a perfect hemisphere, half of a sphere bump, you can get a nice formula for this. You could derive this with Euclidean geometry, like high school geometry. You could find that it's C equals 2 pi, not times R, but 2 pi times the sine of R. The sine graph lies below the line y equals x, so it's growing slower than the area in Euclidean space. But you could do the same on a surface like a saddle, a surface that bends up in one direction and down in the other. Now, larger and larger circles, their circumference moves up and down as the space is twisted. And the circumference is greater than 2 pi r. In fact, in a really symmetric version, you get 2 pi times the hyperbolic sine of r, basically exponential in radius instead of linear. And we'll use this sort of characterization to understand space, to characterize different types of space. When a surface has circles growing quicker than they do in the geometry of the Greeks, we say the space is negatively curved. When we have a space where the circles grow slower than in Euclidean geometry, we say the space is positively curved. And this quantity is really, we want to talk about curvature at a point. This is where you're standing. You want to know how much space differs from the geometry of the Greeks. So I don't care about circles far away. I'm trying to measure circles as they get really close to me. Mathematically, we do that with a limit. So the precise definition is you can take the difference between the Euclidean circumference and the circumference you measure, divide by some normalization, and take the limit as your circle shrink to 0. This will give you a precise number that you could calculate on any surface, and it will tell you how curved the surface is at that point, how much that differs from the geometry we grew up with. And since this is a local quantity, since this is a quantity that is just defined at each point, a general surface has different curvatures all over the place. So here I drew some surfaces and I've colored them by their curvature. The redder a point is, the more positive curvature there is, the more it looks like the top of a hill. The more purple a point is, the more negative curved it is, the more it looks like a saddle. And the more green it is, the closer it is to being able to be flattened onto the plane, the closer it is to following the laws of Euclid. So general surfaces are messy, but as mathematicians, we often like to pick the simplest objects we can first and really deeply understand them. So instead of dealing with surfaces like this, we're going to focus our attention on surfaces that have the same curvature at all points. We also see these in the real world. There's zero curvature surfaces all around us, the walls, the floor, the ceiling. I was in a room with a curved ceiling earlier, so I had to check. There's positive curvature objects. Object with a constant positive curvature is a sphere. And negative curvature is we're a little less familiar with, but there's a lot of biological examples. Corals, some of the skin of invertebrates, the leaves of kale, and so on. Things that crinkle like this because they're growing so quickly they struggle to fit inside of space. Of course, these are real world objects, and in mathematics, we like to make things precise. So we make precise idealizations of these. A perfect space of positive curvature is the perfectly round sphere, the unit sphere, set of all points distance 1 from the origin. Zero curvature, perfectly flat Euclidean plane. And negative curvature is a space called hyperbolic space. This is a map drawn of hyperbolic space. We can't see it very well. It grows so quickly, it's hard to fit large chunks of it in space around us. So we draw a map, much like we draw maps of the Earth on the plane. So we'll see a map like this a couple times. The important thing to notice when looking at this map is that all of those angels and demons in this print of Escher are the same size in hyperbolic space. So just like Greenland on a map of the Earth looks too big, like it looks like it's almost the size of Africa, even though Greenland's really small compared to Africa. On the Mercator projection of Earth, objects near the top and the bottom are larger than you'd expect. On this map, it's the reverse. Things near the edge look smaller than you would expect. They're actually all the same size. But these sort of things also exist in 3 dimensions. We can't see 3-dimensional space around us in front of us, like we can see a soccer ball or a cable leaf. But we can reason by analogy and make precise mathematical spaces. A flat 3-dimensional space is, well, the space around us to a good approximation. We can write down a precise thing by writing down 3-dimensional vector space, an inner product. To build a space of positive curvature, a 3-dimensional space that's positively curved everywhere, we reason by analogy. We say, how could you make the space we know in 2 dimensions, a sphere? Well, if you slice a sphere into slices, what do those slices look like? The top slice, you hit the sphere, it's a dot at the North Pole. As you continue to slice it, you get wider and wider slices until you get to the equator. And then the slices get smaller until you get to the South Pole, where there's another point. So how could we reason by analogy? We could take all of those slices and raise the dimension by 1. Well, point stays a point, but all of the circles become spheres. So we could start with a point and then make an increasing size sphere until we get to a larger sphere, decrease that down to a point. And then by analogy, what do? We just stack them on top of each other. Of course, just is hiding a lot here, right? Like we have to stack them in the 4th dimension, just like we stacked these 2D slices in the 3rd. And so on our poor screen, it looks like they're on top of each other. But when we do this, we get an object in 4-dimensional space that has these 3-dimensional slices. That object is the surface of a 4-dimensional ball. It's the set of points distance 1 from the origin in 4 dimensions. And we call it the 3-dimensional sphere, just like we call the surface of a ball the 2-dimensional sphere. And we can also build a space of negative curvature. How do we do this? Well, we can take our 2-dimensional example we know and love and spin it around. If you do that mathematically, you can write down a space, looks like a ball, and inside of that ball has negative curvature everywhere. And this we call hyperbolic 3 space, just like hyperbolic 2 space was the plan. And we could, of course, do this in higher dimensions, but we wouldn't be able to even draw cartoons of them on the board anymore. Now, what I want to do is try and help us understand how to see these spaces, how to gain some intuition about them without doing all the calculations. If for the mathematicians in the audience, what do we do next? We write down the formulas and we do a lot of examples to convince ourselves how these spaces work. I want to take you on a lightning tour of just the results of a couple of those examples. So first, before I can draw pictures on the board to show you what I mean, we need to talk about what the pictures mean mathematically. How do we interpret pictures of spaces other than the space we live in? And to do so, we need to talk a little bit about vision. So imagine I'm this poorly drawn stick figure, and I'm looking at this poorly drawn ball. How do I see the ball? How does information about the ball get into my mind? Well, it's via light. Actually, in the real world, light's the time reverse of this, right? Light comes from the world into our eye, but often it's easiest for me to think in the time reverse scenario, the way Greeks imagined light worked. There's light rays coming from your eye as a picture here. So all the spots where I see the ball are where light rays hit the ball, connecting the eye to the ball. I know this sounds really pedantic, but it's actually really important to think through what is going on here. The reason is light travels on straight lines in space. It's a property that was pointed out long ago by Ptolemy and even in Euclid's book on optics, derived multiple different times throughout the centuries. And when we switch to curved geometry, these straight lines or geodesics in space will be the lines we will take light to travel on. We will use vision as a way to probe geometry with straight lines. So let's just take this for Euclidean geometry, for the flat 3-dimensional world around us, and think about what this tells us. Light moving on straight lines gives us a connection between what we see in our day-to-day life and the geometry we learned in high school. So here's me looking at that blue ball. Now I'm just this little eyeball, and the blue ball's here. I want to see how big is the blue ball in my vision. I can compute this with trigonometry in the plane, right? I find the light rays that hit the ball tangentially, and that tells me the angular size of the ball in my vision. When I compute that, I get a nice little formula here. And this formula tells us things we already know about the world. It says, well, theta, the angular size of an object in my vision, is approximately twice its radius over its distance. That is, when you move an object twice as far away, it gets half as big in your field of view. Our brains have this built in, like deep, deep in evolution, this was built into us. When I see a person in the back row and they look to be 3 centimeters tall, I don't think, oh my gosh, there's a 3 centimeter person in this room. That's incredible. I go, that person's far away from me. By this formula, I gauge distance with my mind. And in thinking about curved space, we're going to have to undo some of that intuition. That's why we need to point this sort of thing out. The other thing I want to point out now is if vision is going by straight lines from your eye to a sphere, you can think about the set of rays connecting your eye to the sphere as a cone that's tangent to the sphere. The part of the sphere you can see is the part of the sphere that's inside of that cone. That's less than half the sphere. Asymptotically, as you get infinitely far away, that cone starts to look like a cylinder, and that cylinder would allow you to see exactly half the sphere. And so that's why on a photo of the Earth like this is from the Apollo missions, you can see the South Pole, but not the North Pole at the same time. You can always see less than half the sphere. But what does curvature do? When we add curvature to space, positive curvature draws straight lines together, and negative curvature causes straight lines to move apart. In the top here, I have a simulation of looking at the Earth as I change the curvature of space. When the lines are straight, that's the normal Euclidean space we're used to. When the lines bend inwards, that's an effect of positive curvature. When they bend outwards, that's an effect of negative curvature. I want you to think a little bit about what you would see if you were standing there and the geometry of space was changing in this way. How would your view of the Earth differ in time? To walk you through this, I'd like to look at a lower dimensional example. Let's bring ourselves down to the 2-dimensional sphere, space of positive curvature. I want to imagine that I'm standing at the North Pole of the sphere, and I'm looking at this green ball. These yellow rays are rays of light connecting my eye to the ball. Some of the rays hit the ball, some do not. As the ball moves farther away from me, the number of rays that hit the ball changes, because rays of light, lines of longitude, straight lines on the sphere, starting at the North Pole, move outwards until they get to the equator, and then they move inwards and hit the South Pole. What does this green ball look like? Well, at first, when the ball's near me, as it moves farther away, less and less light rays hit the ball, right? What does that mean? That means the ball's shrinking in my vision. But when the ball's far away, when it gets past the equator, what happens? As the light rays move back together, more and more light rays hit the ball. The ball grows in my vision. So what do I expect? I expect to see something like this. I expect to see the ball in front of my face, and the ball shrink for a while, and then grow. If the ball's at distance x from the equator closer to me, or x from the equator farther away from me, it's the same exact size in my vision by symmetry across the equator. This would be a very strange world to play catch in positive curvature. You'd throw a ball away from you, and the ball at some point would appear as though it was coming back at you in angular size, even though it's getting more distant. We can, of course, work this out using spherical trigonometry instead of the trigonometry of the plane, and compute the exact angular size, and the approximate angular size not being 2r over distance, but over the sine of distance. But that's not all the secrets that are hiding here. Actually, look a little closer at this picture drawn, the schematic from spherical geometry. As lines of light move away from each other and are drawn back by positive curvature, where do they hit the ball? They hit the ball on the backside. You see more than half the sphere. instead of less than half the sphere. So what would it actually look like if I threw a ball? The ball would move away. But when it's started to get larger in my vision, it wouldn't look exactly the same as when it was close by. We'd be able to tell by how much of the sphere we see. It's funnier and maybe more illustrative to do this not with a ball, but with a friend. Imagine you're walking away from a friend in positive curvature. What do you see? Well, your friend's face shrinks, just like it does in flat space, to a point. Then your friend's face starts to grow. But you also see more of your friend's face. And more. And eventually, you see all of your friend's face. When your friend is at the South Pole, relative to you, every direction you look, you see your friend. Your friend's ears are to your sides. Your friend's beady eyes are in front. And your friend's hair fills the entire sky behind you. Now, it's fun to do this with chalkboard drawings, but it's even more fun to simulate it. So here's a 3D scan of a person, and here's ray tracing this in positive curvature as this person just backs up from the camera. But at first, their head shrinks, as we expect. But as soon as it stops shrinking, it just gets really, really creepy. I have no more comment. Don't be scared. Your friend's very far away from you, right? You can tell by how big they are. So, okay. Well, that gives me nightmares. Instead, it's perhaps more instructive to imagine seeing the Earth from far away. What does the Earth look like if we sent an Apollo mission to the moon in positive curvature? Instead of just seeing the South Pole, we see here the South Pole and the North Pole at the same time, because we're seeing far more than half the sphere when we're far away. This is the sort of behavior, when you see this in a space, that should make you think, there's positive curvature. I'm seeing more than half of objects. Objects are looking big even when they're in the distance. That's the sort of telltale signs of positive curvature in vision. And so the sort of picture I like to keep in mind is, let's throw a bunch of balls into the space and just let them move around to get a sense of the geometry. All of these balls are the same size. They're all moving at the same speed. For the mathematicians in the audience, this is a collection of spheres inside a Poincare dodecahedral space with its positive curvature metric. But what I want you to notice is the balls in the distance are very large. The balls close up are also quite large. And you see a midpoint where the balls shrink to their smallest. That's the equator. That's halfway across the positive curvature universe from you. This is the sort of picture. When we see this in a mathematical space, this makes us think positive curvature. But I want to think, what about negative curvature? What happens if in positive curvature, lines of sight are converging after some time? In negative curvature, lines of sight are spreading out faster and faster and faster. How would this exact picture change if I switched the curvature to negative? What would happen to a very far away ball? If lines of sight diverge from each other exponentially fast, very, very, very few of them would hit a ball far away. It would look small. Here's the same collection of balls, but in negative curvature. This is in Seifert-Weber space. You can see in the distance a collection of balls that are almost point-like. They're smaller than pixels on my computer screen. And they're not actually that distant. In terms of units of space here, I'm only drawing objects in this view that are as far away as the objects in the last view, in the last picture. I'm only drawing things that are up to 6 units away. The curvature is like that. And so 2 surprising things about that. They look really small, and you see a lot of them. Lots and lots and lots of objects fit into this space. Negative curvature space is very, very, very big. We can do the same sort of thing we did in flat space and in positive curvature. We can work out trigonometry in a negatively curved space to understand this quantitatively. And you see, as lines of sight spread out from each other, we see less than half the sphere, significantly less than half the sphere, as the spot where they're tangent to the sphere is very, very close on the front. So what does the Earth look like from an Apollo mission in hyperbolic space, in negatively curved space? You actually see very little of the planet at a time. Here, the entire hemisphere is taken up by just a piece of Central Africa. We'll pass over South America, and the Caribbean. The world is large, but you see very, very little of it as light rays spread out. So these are the characteristic properties of negative curvature. Things look small very quickly, and you see very little of any object you look at. I want to emphasize just one more time just how big negative curvature space is. In flat space, we're used to stacking cubes. As kids, you have blocks that you can build with, and you could build a big cube out of smaller cubes. When you do so, there's 4 cubes around each edge. So you stack them, just like there's 4 squares around each vertex tiling the floor. In negative curvature, many more cubes can fit around each edge because there's just more space. So starting with 1 cube, building out the nearest neighbor cubes, the next nearest neighbors, and the next, we notice the number of cubes is growing more exponentially. And so here's a view from inside that sort of a cubical tiling. You can see just how many cubes fit in a negatively curved space. But actually, so this is our view of, we've seen positive curvature. Well, we all live in zero curvature. And now we've seen negative curvature. So we have a sense of what each of these spaces look like. But this isn't the end. This is just the beginning of the new mathematics that has come out of taking curved spaces seriously. Perhaps the simplest thing you could invent yourself after seeing these spaces is a space we call, quite unimaginatively, H2 cross R. What is this? This is a stack of hyperbolic planes. If you take negatively curved spaces and you just stack them on top of each other, you'll get a 3-dimensional space that has negative curvature in 2 of the directions, namely the spaces you stacked, but it has 0 curvature in the other directions. If you take vertical slices of that space, those vertical slices are Euclidean flames, they're flat. So this is a space where it's differently curved in different directions. And we can see from the inside, if you were in a space like this, we can use our intuition from learning about negative curvature, learning about 0 curvature to pick out these directions visually. When I look here, I see a bunch of really, really small, skinny, weird-looking balls in the distance. They're very small very quickly. That tells me there's probably negative curvature in that direction. And now as I look towards where the words are at the top of the screen, I see in that direction, the balls actually don't shrink so fast. That reminds me what happens in our world, where something twice as far away is only half the size. That says, that direction, that's where there's 0 curvature. Those are the vertical slices. This is how we can bootstrap our intuition from those easy spaces to more complicated spaces. And just like we can stack a collection of hyperbolic planes, we can also stack a collection of spheres. Again, you can't do this in 3D. You need to stack the spheres in 4 dimensions. But when you stack spheres of the same size on top of each other, you get a type of a cylinder. This has positive curvature in 2 directions, in the sphere direction, and it has 0 curvature in vertical slices. What does this look like? Well, that direction has 0 curvature, right? The balls aren't shrinking very quickly. What about in the direction towards the top of the screen here, where the balls are getting very, very large? When something looks very large in the distance, that is a signature of positive curvature. That tells us just from looking at this picture, even if we don't understand the precise geometry of the space, we can say, aha, there's a direction of positive curvature, there's a direction of 0 curvature. And while we won't get into them today, there's a lot more interesting spaces in this direction. Here is the intrinsic geometry of a 3-dimensional space called SL2R. It's a Lie group that shows up in the type of geometries, these homogeneous geometries, that's the same at every point. I want you to look at this and see, what do you think the curvatures are? What do you think is going on here? So there's an area here where spheres are getting really big and warped and scary. That means positive, right? And then there's a direction where the spheres are getting really, really tiny, really fast and stretched out. That means negative. This is a type of space we haven't seen yet. It's one with a mixture of positive and negative at the same time. Okay. So for people who are interested in these sort of animations, want to see more, quick shout out to me and my collaborators, wrote a paper on how to draw these sort of pictures. For any mathematicians here, I'm around through Tuesday. I love talking about this stuff with people. If anyone wants to hear more of the technical stuff, like how this works, let me know. I'm more than happy to talk about it. But a lot of the things I'm interested in all relate to this modern notion of geometry. That's the end of the main part of the talk. What is our modern view of geometry? Where I see myself is as somebody who likes basically anything that touches what I just showed you. So here's out of a collection of my interests, I want to just quickly share a little bit about two of them, two spots where geometry has changed the world a bit. Let's see how I do here. The first is an application to pure mathematics, understanding spaces. What types of space can there be? How many ways could an abstract mathematical space be curved and twisted and tied up in knots and so on? And it's a hard problem because there's a lot of spaces out there. Like what we usually do in math, we start with the easy ones first and hope that that helps in 2 dimensions. What are the easiest things? There's spaces we can parameterize. There's spaces we can write down a parameterization, a function that wraps up some space we understand. Like the torus can be made by wrapping up the plane. We understand the plane very well. It's a nice flat geometry. And we can understand the torus by rolling up the plane. And we learned in the 1800s that we can do the same thing with other 2-dimensional spaces. If you cut out an octagon from negatively curved space, you can roll that up into this surface called the genus 2 surface. And in fact, the uniformization theorem from the beginning of the last century says that every surface comes from some rolled up geometry. We can use geometry to understand every single surface. Extending this to 3D, we see at first sometimes this works. Some 3-dimensional spaces are rolled up from geometries we understand. A 3-dimensional version of the torus, just like the torus was a square that's been rolled up, a cube that's rolled up is the 3-dimensional analog. And that unrolls into flat Euclidean 3-dimensional space. Instead of rolling up an octagon, you can roll up a dodecahedron in negatively curved space to get a 3-dimensional closed manifold. And after the success in 2 dimensions, you might hope this is going to work. Maybe there'll be a theorem that says every 3-dimensional space is a rolled up space, just like we had before. But unfortunately, this fails for an interesting reason, a reason that kind of looks like wormholes. If you take 2 spaces, each of which roll up from some geometry, and you build a wormhole between them, you scoop out a ball from each space and you glue them together, so you could teleport from one to the other by walking through this tube. That new space doesn't unroll nicely anymore. This is for the interest of math people in the audience. I've been interested in trying to draw pictures of this sort of behavior recently. So here's an image from the connect sum of 2 3 tori, where the 3 tori have different Euclidean structures. And you can see, we'll wait for one to come back. Here we go. A little wormhole passing by. This is a tube into the other side, the pink side of this picture. We're actually tracing out this green loop right here in space. Here, it'll take us through the tube quick. So this is going through the wormhole from the blue space to the pink space. This is a space that doesn't unroll nicely. But what we've learned through a result known as the geometrization theorem now, proved by Perlman in the early 2000s, is that while all 3-dimensional spaces don't unroll as nicely as they did in 2D, geometry is still really important in 3 dimensions. Namely, 3-dimensional spaces are built like Legos. They're built out of 8 types of geometry that are glued together by 2 types of wormhole connections. The one I just showed you and another one that are built out of tori. So these 8 building blocks are called the Thurston geometries after William Thurston, who conjectured this result. And just wanted to share a bit about this here because it was actually me learning about this stuff in graduate school, trying to learn about different geometric structures, learn about different geometries, that I came across a paper written by Anna together with Daryl and Jeff that really started me down the trajectory I went on today. So thanks for inspiring my PhD. And then in just the last couple of minutes, I want to share something I think is pretty exciting, a new application of these ideas. Once we understand modern geometry deeply, once we really have in our mathematical toolkit the ability to think about spaces of different curvature and reason about them, we can bring this to application in the real world quicker than I thought. So I want to talk just briefly about a really interesting project done here at HITS in data science with graphs. So what's a graph? You can think of the vertices are representing some sort of data we have. Edges are some sort of relationship between that data. The one example I'll use in a minute here, the vertices are actually going to be court cases, and the edges are when court cases have cited each other. So you can kind of build like a legal search engine. Lots of times when you have data like this, you want to compute things about that data. You want to compute relationships, like how close are these two green things to each other in this graph. The way we compute distance is we measure the length of paths between them, and we look for the shortest path. So there's a path of length 4, there's a path of length 3, here's a path of length 2. That's the shortest path here. So we say the distance is 2. Now, that computation is hard to do, because if you have a big graph, you have to do lots and lots of computation. You have to look for the right path. And this is where there's a nice use of geometry. Sometimes a graph, just an abstract collection of dots and edges, actually secretly looks like a space we know, fits nicely into, say, the Euclidean plane. Our graph looks like a grid. In this case, if you can fit the graph into space, you can now measure the distance between two vertices without doing a complicated computation. You can very accurately approximate it by just using the distance in the plane. That's an easy formula, right? Square root a squared plus b squared. To give us a very good approximation of the graph distance. Let us save ourselves a lot of work. And that's very exciting until you confront the hard truth that not all graphs fit well in the plane. Here's a tree, graph with no loops, not connected up, that does not fit well in the plane at all. You can see that because these two vertices here are far apart in the graph, they're distance 4, but they're close in space because the tree grew too quickly. There's too many pieces. We can't spread them out quick enough. But wait, that's the problem. There's too many pieces. It's growing too quickly. We can't fit it in space because there's not enough space. What that should tell us is we should pick something with more space. The tree fits fine in hyperbolic geometry, where each of these pentagons is the same size. Now we can measure the graph distance using the hyperbolic distance to get a good approximation. So our first graph looked like the Euclidean plane and it fit. Our second graph did not look like the Euclidean plane and it didn't fit, but that was okay because we found a new space. Yay. But it's not all good news. This new space doesn't cure all of our problems because our original graph doesn't fit in this space. It's too connected. It's too small. Space wants to expand inside of the graph. And then the real problem is real data is complicated. Like real data doesn't just look like one of these trees or one of these grids. Here's the legal cases and citation graph, where you see there's a lot of interconnections and then there's a lot of these tree-like pieces at the ends. Here's a small piece of that graph. There's a little piece cut out so we can visualize what's going on. Some pieces are highly connected, some pieces are not. This graph has some troubles. It has kind of the best of both worlds and the worst of both worlds. It doesn't fit in flat space because it has a tree, and trees don't like flat space. But it also doesn't fit in negative curvature because, well, it has a grid, and grids don't like negative curvature. So we need geometry that's more complicated. We need something that has negative curvature for the tree to spread out and feel at home. And we need zero curvature for the grid to feel at home. And we've already seen a space like that, right? We had the stack of hyperbolic planes. That's the lowest dimensional example in large collections of spaces, non-positively curved symmetric spaces. And so some work that I've really honored to be a part of here at HITS by a large group of us over the last couple of years, many, many pandemic Zoom meetings at inconvenient times for all. Thank you all so much for your putting up with the 9 time zone difference, has worked on this stuff. And it's been just a really, really fun, interesting, and hopefully useful diversion, bringing geometry to a new world. So with that, I want to say thank you so much.